Hi everyone and welcome back to week 2. This week we will show you what mathematical proofs are, why we need them, and what types of them there exist. The goal of the week is that you will be able to prove formulas easily. In this short video we will recap mathematical notations that are useful for dealing with proofs. This includes a recap of transforming formulas and an introduction to sums and products. Let's get started. In the field of mathematics, we often have to deal with formulas or statements that we need to prove. This means that we want to show that two terms are, for example, equal, or that one is smaller than the other one, and so on. Basically, any mathematical concept that you know can be proven. As you maybe know from other math courses at university, proofs are essential for understanding why such concepts hold. This is the reason why we will talk about proofs in detail this week. But first of all, let us start with a recap. The basis for working with proofs is that we know how to work with formulas and how we can transform them. If you already feel comfortable with this, you can skip the next few slides and go on until slide 7. If not, this short recap might be useful to you. So let's say we have a formula. Generally, it holds that if we perform an operation on one side of the formula, we also have to do it on the other side. In this little example, we want to get rid of the 2 on the left side, so we divide by 2. Consequently, we also have to divide by 2 on the right side in order for the equation to still be equivalent. Now let us shortly recap what happens for which operation under which circumstances. For an equation, it holds for addition, subtraction, multiplication and division that everything we perform on one side, we also have to perform on the other side. For inequations, however, this is a bit different. There's one exception, namely if we divide or multiply by a negative value. This results in a change of the symbol direction. But besides that, everything is the same. So always remember, what you do to one side, you also have to do to the other one. Now is the chance to practice it a bit if you want to. It's a good training to get back into transforming formulas before diving into proofs. You can find all the solutions with the respective steps on the next slide. Here you go. Now you should be ready for working with formulas. Let's continue now with sums and products. A sum describes the addition of several terms. These terms are called the summand or addends. Sums can be expressed with this sum sign, and they basically describe a rule of what their summands are. On the bottom, you have I or k equals m, where m is the starting point. On the top, you write the ending point. Both have to be integers, and the sum iterates in integer steps. So for each step, you use the current I, and as a result, you add all these terms. In this general notation, this means that the first addend is am, the second one am plus 1, and so on until an. As this might be confusing, let us take a look at some examples. Here, the first sum starts at I equals 1, runs until n, and describes the addend by simply I. This means this sum's first element is 1, then 2, then 3, and so on until n. You can see that all you have to do is to plug in I each time. The same holds for the second example, where we iterate over I squared, meaning we add 1 squared, 2 squared, 3 squared, and so on. Another example is the sum from I equals 0 until n of 3 to the power of I. This time the sum starts at 0 and not at 1, but the rules are still the same. We plug in the value for I from the starting value onwards. Now comes the more tricky part with sums. We often want to change the notation of them or shift them somehow. This is a general idea which finds a lot of application in proofs. But if we change the notation of a sum, we have to make sure that the resulting term is still the same. The graphic here should give you some intuition for it. You can imagine that the yellow circle is a bag of all summands of our sum. If we add an element to this bag, we have to remove it again somewhere else in order for the terms to be equal. This is the same the other way around. If we remove an addend from the sum bag, we have to add it afterwards so that the result is still the same. Let us take a look at this in mathematical terms. There are several rules based on the idea of the figure you just saw. The first one is removing the first element from the sum. Formally, this means that if the sum started at I equals m before, we want it to start at I equals m plus 1 now, so that the first element is excluded. Consequently, we have to add it again outside of the sum. In the formula, this is the element am. In the example here, you have the sum from I equals 1 to n of I. So this would be 1 plus 2 plus 3 plus 4 and so on until n. If we want to exclude the 1 from the sum, we simply write this element outside of the sum and let the sum start one element later. The idea is similar for adding an element in front. If we set the start of the sum 1 down, we have a new element inside the sum, which we have to remove outside of the sum again. Formally, if the sum started at I equals m, we now start at I equals m minus 1, so that the element with one I lower is included. Outside of the sum, we subtract this exact element, a m minus 1 again. An example is the sum from I equals 3 to n of I, which would be 3 plus 4 plus 5 plus 6 and so on until n. If we want to add a lower element in the sum, we have to lower the starting point, so we start at 2 now, but also have to remove the resulting element from the sum. So outside, I mean. Therefore, they cancel each other out, and we still have the same result. Now, let's take a look at what happens if we add or remove the last element of a sum. This will especially be important for later proofs by induction. In the case of removing the last element, we lower the upper boundary of the sum. So this element is excluded. Here we lower from n to n minus 1. Consequently, we add the excluded term for I equals n outside of the sum. When adding an element at the end of the sum, we increase the upper boundary by 1. So the sum does not end at I equals n now, but runs until n plus 1. To cancel this newly added term out, we have to subtract it outside of the term again. If you struggle with these concepts, feel free to take a moment and look at the examples in detail. The last two rules for sums you may need are shifts inside of the term. This means that we change the expression inside of the sum sign and replace each I there by e.g. I minus 1 or I plus 1. In order for the sum to still express the exact same thing, we need to adjust the limits now, meaning that the starting and the ending point need to be adjusted. In the example of the upwards shift, we want the I to be an I plus 1 now inside the sum. This means we lower the starting and ending value by 1. Think about this. If we plug in the first element now, we have 0 plus 1, which is 1, exactly like before. And if we plug in the last element, we have n minus 1 plus 1, which is 1, also like before. So the sums express indeed exactly the same thing. For downward shifts, this works also the same. If we lower all i's inside the sum by 1, we have to increase start and ending value by 1. This should have given you an intuition about sums and how to understand and work with their notation. Let's continue with products now. A product describes the multiplication of several elements. These elements are called the factors. A product is written with this sign and basically works the same as sums, only that the terms are now multiplied instead of being added. The notation of having a starting point I equals m and an ending point n is also the same. Obviously, we also have the I here again as the parameter we iterate over, again in integer steps. Intuitive examples of products. The product from I equals 1 to n of I equals 1 times 2 times 3 times 4 and so on. The same holds for the square version as well as for 2 to the power of I. We plug in the value of I, starting with the starting point, then increasing it in integer steps until it reaches the ending point. All elements are multiplied. Now also to the more tricky part with products. We often want to change the notation of them and shift them somehow, like you just learned with sums. But if we change the notation of a product, we have to make sure that the resulting term is still the same. The graphic here should give you some intuition for it. You can imagine that the yellow circle is the bag of all factors of a product. If we add a new element to the spec, we have to remove it again somewhere else in order for the terms to be equal. In this case, this means dividing by it so that the terms cancel each other out. This is the same the other way around. If we remove a factor from the product spec, we have to add it afterwards, meaning multiplying by it, so that the result is still the same. Let us take a look at this in mathematical terms. Working with products is very similar to working with sums. If we remove the first element from the product, so we let it start at m+1 instead of m now, we need to multiply this lost element outside of the product. The example here should make this clearer. If we have the product of all integers starting with the 2 and take the 2 out of the product sign, we need to multiply it by it outside of the product so that the result is still the same. This also works the other way around. If we include a new element in front, so we lower the starting value I equals m by 1, we multiply by one more element inside of the product. In order to end up with the same result, we need to divide by it outside of the sum. In the example, we have the product of all integers starting with 3. If we include the 2 now, we also have to divide by it, which is the same as multiplying by 1 divided by 2, so that the terms cancel each other out. The principle are really the same as for sums, just that the operations we need to use are different. The same applies for the last element. If we remove it, so let the product end at n-1 instead of n, we need to multiply it by it outside of the product in order to get the same result. In the example, we have the product of all integers from 1 to n, so 1 times 2 times 3 and so on until n. If we take out the last element, this means we only multiply until n-1, so not until n anymore. Consequently, we need to multiply it by it outside of the product. Then the terms are equal. For adding an element at the end, so that the product not end at n but at n+1, we need to divide by this new element. Again, the example here shows that if we add a new element to the product, this time the n+1, we need to divide by it as well, so we multiply by 1 divided by n+1, leading the terms to cancel each other out. Shifting the term inside of a product works like this. If you decrease or increase each I in the term inside of the product by 1, you also have to adjust the boundary values, so the starting and ending value. The examples should make this clearer. If we have the product of all integers I from 1 to n and change it to the product of I+1, we need to lower the boundaries by 1, so that the result is still the same. If you plug in the values, you will see that they are indeed the same. When plugging in a 0, the first element is now a 1, as it was before. This goes so on until the last element, where we plug in n-1 and end up with n-1 plus 1, which is n, exactly as what we wanted. This also works the same the other way around. Lowering all i's by 1 inside of the product needs to be adjusting by increasing the starting and ending value by 1. You might ask yourself why we need this at all. First of all, it is good to get a general understanding of sums and products. You will see them quite often and therefore should be able to read them and understand what they express. They are quite often used in formulas, such as the sum from k equals 1 to n of k is equal to n times n plus 1 divided by 2. Or that the product from k equals 1 to n of 4 to the power of k equals 2 to the power of n times n plus 1. This week we will learn a lot about proofs, and you can see the proofs for these two formulas in the video about proof by induction. To test your understanding of sums and products, I prepared some exercises for you, where some kind of transformation has been applied and you have to think about what this means for the rest of the term. As always, the solutions can be found on the next slide. Here you go. I hope that this helped you getting a general understanding of sums and products and a recap of how to work with formulas. Now you should be prepared for the proofs which are to come in the next videos. I hope you liked this one and see you again next time.